In this video, we'll be going over how to determine the electric field strength due to a uniformly charged circular arc. In this example, I'll be using a semicircle, which is, like I said, uniformly distributed charge, which is positive. The first thing I like to do with a problem like this is look at it conceptually. Basically, the idea of taking a small piece and then adding it all up is basically what an integral is. So by defining a small part of the entire semicircle as ds, or a small part of the arc length, with a small charge dq, we can add up all these many pieces to get the overall, or the net charge acting on the point on the origin. You can also see that I've defined d theta and theta, which will be used in solving the problem, and that the force due to dq is pushing in the third quadrant. One thing that's noteworthy in a problem like this is that you can see if you take the mirror image across from dq, that it'll have the same magnitude except it'll be pushing in the other direction, or into the fourth quadrant. So you'll notice that if you resolve the vectors into the x and y components, that the x components cancel and the y components in the same direction would be the resulting force. With that in mind for later, we also know that the linear charge density, also known as lambda, equals q divided by s, which is charge divided by arc length. So with this, we also know that lambda equals that small charge defined earlier over that small arc length defined earlier. And with simple algebra, just by multiplying both sides by arc length, we see that ds times lambda equals dq. From past math classes, we also know that arc length equals radius times theta. So with that, if we take the small length, we know that that's equal to the radius times that small theta, which was defined earlier. Holding on to these ideas, we can start to set up the base equation, so to speak, using two equations found on our yellow equation sheet. By multiplying the low equation by charge, we can get Fe on the same side, and then set the two equations equal to each other. By doing so, we ultimately get E equals 1 over 4 pi epsilon naught times Q divided by R squared. When putting this in terms of the variables defined above, we get dE equals 1 over 4 pi epsilon naught times dQ, or the small charge we defined earlier, divided by radius squared. We can then use the equations that we determined earlier, and we can plug in for dq for ds times lambda. Once we do this, we can then plug in for ds with the second equation we derived, which is ds equals r times d theta. So when we replace the arc length, or ds, we plug in r times d theta, and we get the equation listed below. By doing so, we notice that we have an r and r squared, which means that the r on top cancels with the r squared on the bottom, resulting in only one r, or the radius, on the bottom. It's also important to remember that we're only taking into account the y component of dq because the x components cancel. In order to incorporate this into our equation, we need to multiply what we have by sine theta. Now that we've done this, we are ready to finally take the integral. But before we take the integral, we want to make sure we move all the constant to the left-hand side. We know we can pull out lambda because it's linear, so it will remain constant. This leaves us with taking the integral of sine theta times d theta, which is the small piece of theta that we defined earlier. Due to the fact that we have a semicircle, our upper and lower limits will be pi and 0 respectively. We know that when we take the integral of sine theta times d theta, we'll get negative cosine. For those of you who are not in calculus or have not already taken it, one thing that helps me is if I look at what the integral would be and then take the derivative of that to make sure that it checks out. So in this example, the derivative of negative cosine would in fact be sine. So I've done the integral correctly. As we evaluate this integral, we get negative cosine pi minus negative cosine 0. We know that negative cosine pi equals negative negative 1, which is 1, and we know that a negative minus a negative is positive, and cosine 0 is just 1, which ultimately yields 2. Now that we've evaluated the integral, we can see that the resulting 2 cancels with the 4 on bottom, giving us 1/2. We have now arrived at our final form. E equals lambda over 2 pi epsilon naught r. Although we were just evaluating for the final equation, as a side note, if you're solving for a numeric value, you can always plug in q over s, or charge over arc length, for lambda, or q divided by, in this case, pi r.